Greetings, I'm Squared here, and we are going to talk about learning Circuit 4, which is chords and arcs. So it's these last four on your theorem sheet that we're going to talk about today, so I'm just going to run over them with you, but you should have your theorem sheet out next to you, because I'm going to ask you, what theorem are we talking about, so that you can have it. So this says if two arcs in a circle, or in congruent circles, are congruent. So we know that the arcs are congruent, then we know that these chords are congruent, the chords whose endpoints are defining that arc or intercepting that arc. And the converse of that is true as well. If you knew the two chords were congruent, you would know the arcs are congruent. So if arcs are congruent, then the chords that help make them are congruent, and if the chords are congruent, the arcs are congruent, vice versa. Alrighty. Next one. And again, you have the theorem and the converse, the theorem and the converse. So if chords are equidistant from the center, that means they're the same distance. That's why you have these little marks here to show that that distance is the same. Then these chords are congruent. So if the chords are the same distance from the center, then they're congruent. The converse of that says if the chords are congruent, then they're the same distance from the center. Then these last two kind of go together. It says if a diameter is perpendicular to a chord, so here's your diameter, it's perpendicular to this chord AB. If that's true, then it actually bisects that chord. So that means AE would be congruent to EB. And the converse, if the diameter bisects a chord, you know that it is perpendicular to that chord. And this one says if a chord is the perpendicular bisector of the chord, which is basically just restating this. If it's a perpendicular bisector, we know that it goes through the center. So this one doesn't say it's the diameter, so you could use something like this to prove it's a diameter. Okay, so we are going to do some problems. So have that theorem sheet out, and you are going to figure out which theorem we have to use. Keep in mind that it might be a theorem that we've learned a while ago, or it might be one we just learned today. I love to have my highlighter out when I do this, because when I see a diameter or a radius, I just want to notice that. So I see a radius here, I see a radius here, and I see a radius here. So the confusing part sometimes is when you learn new stuff, you think that that's the only stuff that will apply to a particular problem. For example, in this case, we see that we have a radius, which of course, if we continued it, would have been a diameter, that's perpendicular to a chord. Well, our theorem said that if that's true, then this part's equal to this part. But that's not x. It's not asking us for x. So although that's true, it doesn't help us find x. So this is a little simpler than it looks. And I give this to you because I want you to be on the lookout for simple things. This is a radius, and that's a radius. So if that radius is 13, in the same circle, all the radii will be 13. So x is equal to 13. So it's a little bit easier than that one may have looked to start with. Okay, next one. So on this one, again, we see a diameter that's perpendicular. So we're thinking it's probably that theorem that says if a diameter is perpendicular to a chord, then it bisects it. Well, that helps us in this case, because that means this part is equal to this part. And since that's 12, then we know that x has to equal 12. So you might have spotted that one. Okay, this one. Since we know that these two distances are the same, the theorem that we learned says that the chords would have to be the same. If they're equidistant from the center, the chords are the same. If the chords are the same, then they're equidistant from the center. So we would use the equidistance, then congruent chords. So we would actually just say, oh, well, then those chords are congruent. Let me set them congruent to each other, or equal to each other, and solve the resulting equation. So if I add 7 to both sides, I get 42. And if I divide both sides by 6, I get x equals 7. So in this case, x is 7. Alrighty, over here, again, I'm going to get out my calculator, my highlighter, and I notice that that's a radius. And I also notice that this is the radius. Well, they didn't tell me what this radius was, but they tell me what the whole diameter is. So if I want to find the radius, I've got to take 23.8 and I've got to divide it by 2. That's going to give me my radius, which would help me find this, which is going to help me find this, because this is a radius. Again, it's perpendicular, but I don't need to know that this is equal to this. That's 10.9, so this is 10.9. But they didn't ask me for that. They asked me for this little piece of the radius. So I've got to know what the whole radius is, and then I take 7 away from it, and that helps me find it. So 23.8 divided by 2, 2 goes into 2 once, goes into 3 once with 1 left over, so it goes into 18 9 times. So I've got 11.9. I need to take 7 away from that. And when I say 11.9 minus 7, I get 4.9. So x is equal to 4.9. Alrighty, moving on. So if you have your theorem sheet, this is where you could pause and say, I wonder which theorem I'm talking about. So I noticed that two chords of one circle are congruent. And the theorem told me that if that happens, that it lays off equal arcs. So I know those two arcs are equal. Well, I know this arc is 120. I know that all the way around a circle is 360. So I know that x, if we call that x, plus x is going to equal, plus 120 is going to equal 360. So if I take 360, subtract 120, I get 240. And I know that those are both the same, so I just divide by 2. And I find out that arc dB is equal to 120. And so would arc AB. I didn't write down what you were supposed to find, but you were supposed to find the arcs. Okay. So on this one, we notice again a diameter that's perpendicular to a chord. It makes these two congruent because it bisects the chord. It also bisects the arc. So those two are going to be congruent as well. So we just have to set up two equations. 3x minus 4 equals 5x minus 18 to find x. And 2y plus 1 equals y plus 4 to find y. So over here, when I subtract y from both sides and subtract 1 from both sides, I get y equals 3. Here I subtract 3x from both sides, add 18 to both sides, which gives me 14. If I divide both sides by 2, I get x equals 7. Okay, we're kicking it up a notch, and this time we are asked to find x, but notice we have an x squared. So again, which theorem are we using? The diameter is perpendicular to a chord, which means it bisects the chord. So it cuts it into two congruent parts, which means x squared is equal to 8x minus 15. And you should by now be recognizing that that is a quadratic equation. And to solve quadratic equations, there's multiple ways, but the two we use most often are the quadratic formula and factoring. So if I get everything on one side, which is how I start to solve a quadratic equation, I then check to see if it's factorable. So I want to know, since a, this number that sits in front of the x squared, if a is 1, then it's just what two factors of 15 add up to negative 8. And there are actually two factors of 15 that add up to negative 8, negative 5 and negative 3. So that helps me if it's factorable. And then I use my 0 property, because if x minus 3, which represents one number, times x minus 5, which represents another number, if I multiply those together and get 0, then obviously the only way to get 0 when you're multiplying is if one of those is 0. So I try to say, hey, well, what number gets me a 0 there, and what number gets me the 0 there? 5 minus 5 gets me 0, and then it wouldn't matter what this was. If I put a 5 in there, it's 2, and 2 times 0 is still 0. 3 minus 3 is 0, so 3 times, if I put a 3 in there, that would be a negative 2. So 0 times negative 2 is still 0. So then I should always check. When I solve a quadratic equation and I get two answers, I should always check to make sure it works. So we want to see if I plug 3 in for that x and 3 in for that x, am I getting the same thing? So if I'm checking 3, I'm getting 3 squared, which is 9, and then 24 minus 15. And that is equal. 24 minus 15 is 9, so that checks. So now I need to check the 5. 5 would give me 25 equals 40 minus 15 when I plug a 5 in for both x's. And there again, it works. So yes, indeed, I have two answers, and they are 3 and 5. Alrighty, this one's another equation to solve. Equidistance means equal chords. So same distance from the center, then the chords are equal. So I have 14 equals 5x minus 6. So if I add 6 to both sides, I get 5x equals 20. If I divide both sides by 5, I get x equals 4. So we have a few more, 4 more that we're going to work on today. So I'm going to zoom out a little bit. On this particular one, I noticed that diameter is perpendicular to a chord, which makes x and y equal. So that makes my job easier. I now know that x and y are going to be exactly the same. And then I'm going to highlight my radius and notice that I have another radius there. Now, if you didn't notice that already, you want to make sure you start to notice things like that. So if this is 13, that makes this 13. Because I see a right triangle right here, and now that I have two sides of a right triangle, I can definitely find find the third side using Pythagorean theorem. So I'm going to say 5 squared plus x squared equals 13 squared. Now 13 squared is 169. 5 squared is 25. If I subtract 5 squared from both sides, I get x squared equals, what do I get? 144. And if I square root both sides, I'm finding that x is 12. Well, if x is 12, we already established the fact that since that's the bisector, y is also 12. Alrighty, next. This one, what can we say about this one? Well, let's see. First of all, these two are equal, right? Same distance from the center. That means this chord is equal to this chord. So whatever I get for x, I'm going to add it to 8 to find y. How can I find x? Well, I think about the other one. If I draw this imaginary diameter, it's perpendicular to this chord, which means it bisects this chord. That means x must be 8. And if x is 8, and 8 plus 8 is 16, then y must be 16, because these two chords have to be the same. There wasn't really a lot of algebra to do there, just addition and subtraction, and knowing what theorem to use. Okay, so this one, again, I see this is perpendicular, right? So that means this is equal to this. That doesn't really help me, because I don't know anything about this. So I have to kind of consider what I'm doing here. I notice a 60. Now, why is that important? That's super important, because we have a 30, 60, 90 triangle. So we're going to go back to our 30, 60, 90, 1 root 3 and 2. So what I do, I'm going to get a different color. 1 root 3 and 2. The 1 is opposite the 30-degree angle. The root 3 is opposite the 60-degree angle. And the 2 is opposite the 90-degree angle. We know that because we know that all 30, 60, 90 triangles are similar because of angle-angle similarity, and that the ratio of those sides will always be 1 root 3 and 2. No matter how big or small, the ratio will be the same. So when I come over here and I'm setting up how to find, let's find x first. I'm going to say 6 over x equals 2 over root 3. Because 6 over x, that's what they gave me, and then this is the ratio I know to be true. I'm going to cross multiply, and I'm going to get 2x equals 6 root 3, which means x is equal to 3 root 3. Okay, x is done. Now y, I just remember that y is always, the smallest side is always half the hypotenuse, but let's say you forgot that. Then you could have set it up 6 is to y as 2 is to 1, and when you cross multiply you get 2y equals 6, and so y equals 3. And now the question of, what's the measure of arc AB? Well, that goes back to a few days ago on our assignment where we learned that the central angle is equal to the arc it intercepts. So if that's 60, this has to be 60, and if you drew a little like line, auxiliary line there to show another triangle, this would also be 60. And if that's 60, then this is 60. So altogether, arc AB is 120. That might have been a little trickier because you might not have remembered about the angle. Okay, so what is RT? That's this distance. And what is OM? Again, a diameter that's perpendicular to a chord bisects the chord, and so these two would have to be equal. So RT, if RM is 15 and MT is 15, then we know that RT would have to be 30. Once we know that, well, we could have found OM before that. So OM is going to be a squared plus b squared equals c squared. So I don't know what this is. I'm going to call it x. So x squared plus 15 squared is 17 squared. That's 289 minus 225. And x squared equals 64. And if you take the square root of that, you get 8. So OM is 8. So good luck with that. Make sure you have your theorem sheet out when you're doing the homework so that you can recognize which theorem to go for. And this is M squared, signing out.